My name is Catherine Merck. I'm a senior in high school and I'm taking Calculus 1 as a dual enrollment class. I'm taking this class in particular because my schedule for in-school classes couldn't fit in AP Calc. This video is an adaptation of a project I did for the class, Types of Discontinuities of a Function. Let's begin. Discontinuities are places in a function where, for whatever reason, the function is not continuous, meaning that something created a break in the function, whether a hole, a jump, an asymptote, etc. Sometimes the value of the point of discontinuity is defined, sometimes it isn't, it depends on the function. Limits are often used with discontinuities. The number of discontinuities depends on where you look, but this presentation will cover 5. Continuity at a point is when the function exists at that point, a two-sided limit for that point exists, and is the same as the value of that point. So f of c exists, the limit as x approaches c of f of x exists, and the limit as x approaches c of f of x is equal to f of c. Types of discontinuities. Removable. Removable or point discontinuities occur when the two-sided limit of a point exists, but it doesn't equal the function's value. Removable discontinuities often occur in rational functions with an x in the numerator that has a greater or equal power to an x in the denominator. The discontinuity occurs at whatever value of x makes the denominator equal 0. For example, a rational function that fits the requirements listed above with a denominator of x minus 2 would be undefined at x equals 2. Removable discontinuities can also occur in some piecewise functions where there's a hole at one point and possibly another value for that x-coordinate as long as a two-sided limit does exist. This is the graph of a removable discontinuity. I'd like to point out that the graphs shown do not necessarily match the examples listed in the text. Infinite discontinuities. Infinite or asymptotic discontinuities occur when the two-sided limit doesn't exist because it is unbounded. This happens in functions with vertical asymptotes, such as rational functions where the degree of x is greater in the denominator than in the numerator. The discontinuity exists at the asymptote. For example, in 1 over x minus 2, the function would be discontinuous at x equals 2. Jump discontinuities. Jump discontinuities are places in a function where the left and right limits both exist but are different, meaning that a two-sided limit for that point does not exist. These happen often in piecewise functions where there is a break in the function. For example, a piecewise function with some function as long as x is less than or equal to 6 and another function as long as x is greater than 6, as long as they don't have the same value at the point of the break. Oscillating discontinuities. Oscillating discontinuities occur when, as the function approaches a point, it oscillates between at least 2 points at a faster and faster rate. An example of this is when the sine or cosine is taken of a rational function when the x in the denominator is at a greater power than the numerator. For example, sine of 1 over x minus 2. As x approaches 2, it oscillates more and more quickly between 1 and negative 1. Other discontinuities. Other types of discontinuities exist, such as mixed or even weirder examples, but we won't show them here. Written example, removable discontinuity. So we have f of x and g of x here. We're going to find the points of discontinuity of them. So for f of x, since the denominator of the fraction of f of x equals 0 when x equals 5, the point of discontinuity is at x equals 5. G of x. Since the denominator of the fraction of g of x equals 0 at x equals 7 is the point of discontinuity. So now we're going to find the limit of the two functions at the point of discontinuity. So we take the limit as x approaches 5 of f of x, which is x squared minus 25 over x minus 5. We factor the numerator to get x plus 5 times x minus 5 over x minus 5. We can cancel the x minus 5's, leaving us with the limit as x approaches 5 of x plus 5. So the limit of f of x is as x approaches 5 is 10. We can do the same thing for g of x. So we take the limit of g of x as x approaches 7, x squared minus 49 over x minus 7. We factor the numerator to get x plus 7 times x minus 7 over x minus 7. We cancel the x minus 7's to get the limit as x approaches 7 of x plus 7. So the limit of g of x is 14. Some things to remember when solving a removable discontinuity. For one, keep in mind that while g of 7 equals 10, the limit as x approaches 7 of g of x is 14. A two-sided limit exists for removable discontinuities, and not every rational function with a larger power of x in the numerator has a removable discontinuity. That's just a pattern I've noticed. Written example, infinite discontinuity. So we have h of x and j of x, and we're going to find the points of discontinuity for them. Since the denominator of h of x is x, the value that makes it 0 is 0, so the point of discontinuity / the asymptote lies at x equals 0. J of x is a little bit more work because you have to solve for the denominator, which in this case is 2x plus 4. So we solve that and get x equals -2. The asymptote / point of discontinuity lies at x equals -2. Some notes for solving infinite discontinuities. Limits over infinite discontinuities do not exist. However, some people claim that limits exist for infinite discontinuities and that the limit is either -infinity or infinity depending on which direction the function trends towards. Like I said before, infinite discontinuities are not restricted to functions with a greater power of x in the denominator. Written example for jump discontinuity. So we have k of x and we're going to find the point of discontinuity for it. Since this is a piecewise function and both of the internal functions wouldn't contain discontinuities, we can look at the points where the functions switch, in this case around x equals 5. There's a function for x is less than 5 and x is greater than 5, so we must check the values of the internal functions as x approaches 5 to see if there's a discontinuity, and what kind. This is done in the next section and gives two different values, showing that there is a point of discontinuity at x equals 5 and that it is a jump discontinuity. Example walkthrough for jump discontinuities. So we're going to find the left and right limits of k of x. We're going to start with the left-handed unit, which means we're going to take the function that corresponds to when x is less than 5, in this case 1/3 x. So we're going to replace the x in 1/3 x with 5, so we get 1/3 x times 5. So the limit of k of x from the left as x approaches 5 from the left-hand side is 5/3. The limit of k of x from the right-hand side, we're going to take the other function, which is 2x, so 2 times 5. So the limit of k of x as x approaches 5 from the right-hand side is 10. Notes for solving jump discontinuities. There's no two-sided limit over a jump discontinuity. If there is, it's probably a removable discontinuity. Not every jump discontinuity is part of a piecewise function and vice versa. Written example for oscillating discontinuities. So we have L of x and M of x. We're going to find the points of discontinuity for them. L of x. The point of discontinuity of oscillating functions can be found through the inside function, in this case 20/x. 20/x is undefined at x equals 0, so the point of discontinuity of L of x is at x equals 0. So for M of x, similarly, the inside rational function of M of x can show us where the point of discontinuity is. 1/x minus 2 is undefined at x equals 2, so the point of discontinuity of M of x is at x equals 2. Notes for solving oscillating discontinuities. There is no limit, one or two-sided, for oscillating functions. So, to conclude, discontinuities occur where there is a break in the graph of a function. For the function to be continuous at a point, three conditions must be satisfied. F of c exists, the limit of f of x as x approaches c exists, the limit of f of x as x approaches c equals f of c. Limits are often used with discontinuities. There are four main types of discontinuity, but other types are possible. The possibility of limits over discontinuity over a point depends on the type of discontinuity. Removable discontinuities have both one and two-sided limits possible. Jump discontinuities have only one-sided limits possible, and infinite and oscillating discontinuities don't have any possible limits. Here are my sources. I'll also put them in the video description so the links work. Thank you so much for listening to this.